Hello students, this is Narendra Kumar Devedi welcoming you all in the next lecture of third chapter of first unit, that's electrostatic potential. So as we have gone through electric charge and electric field in the first chapter, now in the subsequent chapter, second, we have seen Gauss's theorem and its applications. Now it's turn to start third chapter, electrostatic potential. So electrostatic potential, first we must have basics of electrostatic potential. What is the electrostatic potential at certain point in the space, that's three-dimensional rectangular coordinate system at any point? What is the electrostatic potential? Let's have basic concept of that. So the first topic under this chapter that we are taking is an important property of electrostatic field. Though we have taken a small concept of electrostatic field in the chapter of work, power and energy, 4th unit, class 11th, under the topic of conservative force. So वहां पे हमने कंजर्वेटिव फोर्स का जो कंसेप्ट समझा था, तो ये चीज समझा था कि जो इलेक्ट्रोस्टैटिक फील्ड है और इसके बाद में जो इलेक्ट्रोस्टैटिक ग्रेविटेशनल फील्ड है, ये दो फील्ड ऐसे होते हैं जो कि कंजर्वेटिव फील्ड्स होते हैं। मींस इन पे जो वर्क डन होता है वो पाथ का फंक्शन नहीं होता है, बल्कि स्टार्टिंग और एंडिंग पॉइंट्स का फंक्शन होता है between those two end points. So let's have this concept now. So the very basic or important property of electrostatic field is, if we take the line integral of electrostatic field over any line segment dl between any 2 points, then it depends only on initial and end points, final point, and does not depend on the path between these two initial and end points, as electrostatic field is conservative in nature. So this needs to be proved. So let's begin proving this. So let me have three-dimensional rectangular coordinate system in which we have the position of source charge plus q at its origin O. Now x, y, z, these are three coordinates that we have. Now suppose we have 2 points here as A and B, and take any arbitrary path joining these two endpoints A and B as L. Suppose the position vectors of these points A and B say RE and RB. These are position vectors, and this is the arbitrary path chosen L between these 2 points or joining A and B. Let me divide this L path in small, very infinitesimally small segments of length, each of length dl. So one such segment is being now considered, and that one such segment is CD, this CD, and this has got length of dl vector along this. Let the position vector of point C be say vector small r, and that of point D be say vector r prime. So these are two vectors, vector r for this C point of small segment of this part L, and this r prime be the position vector of D point of this small segment dl. Now what do? We just now calculate the E dot dl between this path. So vector E function of vector r dot vector dl over this small segment dot delta L, which is equals to, now just place the value of electrostatic field at this point. So this is 1 upon 4 pi epsilon naught q by r square into r cap dot delta vector L. So this is simply the electrostatic field at r distance from this source charge. Now, as we have taken these AB and this path length in the electrostatic field of this plus Q charge. So here, for this R cap, we can have 1 upon 4 pi epsilon naught Q upon R square dot, this R cap can be written as vector R upon R into delta vector L. So this makes R cube. So this is 1 upon 4 pi epsilon naught into Q upon R cube. Now this vector R dot vector L. Now this needs to be calculated. Let me call this equation number 1. We'll be reverting back, coming back to this equation. Now we are approaching towards the calculation of value of this product, vector R dot vector L. So from the figure, from this diagram, actually this, if we use triangular law, so this vector R plus dl has to be equals to this vector R prime. So we now write vector R plus, for the sake of simplicity, we should take this delta L. So vector R plus delta L vector, which is equals to vector R prime. Now here, let's have the square of this. So taking the square now, we have vector R plus vector L dot vector R plus delta L vector, and this will be the value of vector R prime square. Now just open the bracket. So you will be having R dot R square plus R dot L, vector R dot vector L plus vector L dot vector R plus delta L square, which is equals to R prime square. Now as we know, delta L itself is infinitesimally small. If we take the square of it, it will be quite smaller. So just neglecting this term, and as we know, dot product, scalar product is commutative. So this can be written as further vector R dot vector delta L. So this makes twice of this term. So we have now with us R square plus twice of R dot vector delta L, which is equals to R prime square. Now just transpose this term here, so that we have this thing R prime square minus R square, this, which is equals to twice of R vector dot vector L. So R dot delta L vector. Now just dividing both the sides by 2, we have, so this is vector R dot delta L vector, which is equals to half R prime square minus R square. Now further, using the identity a square minus b square, we can have this as half into R prime plus R into r prime minus r. Now as this here we use, since r prime is nearly equal to r itself, so here this can be written as 2r. So with this consideration, we write now it as this to be 2r, and this is r prime minus r into this half. So this thing comes. Now just cancelling this half with this 2, we have r into r prime minus r with us. So just now we can have this value back here in this position. So here now we come back to equation number 1. So here we can write now from equation 1 we have, what do we have? This vector E function of vector r dot vector dl, which is equals to 1 upon 4 pi epsilon naught q upon r cube into. Now see, this value of this product, as we have calculated this to be this one. So just place this value r into r prime minus r. Now this r will be cancelled with this cube, leaving square here. So further we can move ahead and write 1 upon 4 pi epsilon naught, which is equal q upon r square into this thing back r prime minus r. So this can be written thereafter as simplification to this term, this step. Now thereafter we can have here actually this r square can be written as 1 upon 4 pi epsilon naught q upon r into r prime into r prime minus r. Here how did we write? As r equal to r square equal to r into r, which is nearly equal to r dot r prime. With this consideration, this r is replaced by r prime, as it is just nearly equal to this r. So thereafter we can move ahead and proceed like so. Hereafter we come at this thing equal to 1 upon 4 pi epsilon naught q upon this thing r, or else you can write inside it r prime minus r upon r into r prime. So just separating these two terms, we have r prime upon r into r prime minus r upon r into r prime like this, and this is q upon 4 pi epsilon naught. So hereafter this r prime and here from r, so we have q upon 4 pi epsilon naught into 1 upon r minus 1 upon r prime. So this is the outcome of this. And hereafter, what do we write? Hence integral, if we take if we integrate these both sides between this a and b, so integral from a to b, vector e function of vector r dot vector dl. So this gives us q upon 4 pi epsilon naught. This is 1 upon r a minus 1 upon RB. So this is the outcome. As can be seen, this integral of electrostatic field between over any path L bounded by two endpoints A and B depends only on endpoints, not on the path followed. Hence, the electrostatic field is conservative in nature. So, after this, let's move on for the next. Okay, students, so let's have next topic, electrostatic field, a conservative field. So, one property we will be proving here for electrostatic field, that if any field is conservative, so one property that the field has to obey is if we take the integral of that field over any closed path, so that has to come out as zero. हम इस प्रॉपर्टी को यहां पे प्रूव कर रहे होंगे. So let's start. Suppose we have here three-dimensional rectangular coordinate system in which we have the source charge plus q situated at its origin, and say these are three axes x, y and z, and suppose we have 2 points A and B in the electrostatic field of this plus q charge. Now just have one path from A to B. Now this path we represented by say L, and now we have another path from B to A, so let this be L dash, and the position vectors of these two A and B points with respect to origin are RA and this RB. So now let's calculate line integral of electrostatic field over this path, then over this path, and just adding them. So if we have the line integral of electrostatic field over this closed path, so that has to come out as zero. Then only you can say electrostatic field is conservative field. So let's see what comes. So integral over any closed path of electrostatic field as a function of R dot dl, which is equals to, now see, first we take this path, so integral from A to B along L of vector E function of R dot dl plus integral from B to A. Now this from B to A along L dash of vector E function of R dot dl. Now these values we have just seen in the previous topic. We directly write Q upon 4 pi epsilon naught. This will be the common term, and here inside you will be having 1 upon RA minus 1 upon RB for this term, plus here also you will be having Q upon 4 pi epsilon naught into 1 upon now this RB minus 1 upon RA, just having this term as whole common. Q upon 4 pi epsilon naught, this is 1 upon RA minus 1 upon RB, these two terms, plus these two terms now, 1 upon RB minus 1 upon RA. So this gets cancelled with this gets cancelled with this. So as a whole we get a big zero. Hence, the electrostatic field is a conservative field, as the line integral of this electrostatic field over a closed boundary is zero. So this way we can prove. Okay students, let's have next topic, electric potential and potential difference. So to begin with this topic, we directly now use the previously obtained results. I'm just writing now them. So what have we seen now? Integral from a to b since of vector E as a function of r dot dl is just equal to q upon 4 pi epsilon naught into 1 upon Ra minus 1 upon Rb. This we have just derived in the previous topic. Now hereafter we can have in terms of position vector we can write this to be 1 upon 4 pi epsilon naught into 1 upon mod of vector Ra minus vector R naught minus 1 upon mod of vector Rb minus R naught. This expression is in terms of position vectors. So here the left hand side would remain same, integral from a to b of vector E as a function of r dot vector dl. So yes, these are two equations, starting equations with which we are beginning or we are initiating the topic now. So here, what do we do now? As we rewrite these two equations, rewriting these two equations means what? We will be taking this term as first term and this term as second term. So, rewriting the above equations, we have, what do we have? Integral from a to b of vector E function of vector r dot dl, which is equals to, it's just have multiplication of this inside. So we have minus of q upon, or you can write q upon 4 pi epsilon naught into 1 upon Rb minus, no, not minus, plus q upon 4 pi epsilon naught into 1 upon Ra, and here you can have integral for the second a to b vector E function of vector r dot dl, which is equals to, we take this term as first one, so we write minus of q upon 4 pi epsilon naught into 1 upon mod of vector Rb minus vector R naught plus q upon 4 pi epsilon naught into 1 upon mod of vector Ra minus vector R naught. So this is simply the interchange of terms. The second term has made the first term and the first term has been made as second term. This is simple exchange of terms. Now just moving ahead, we can further write, if we now just take point A to be at infinity, where the potential is supposed to be 0. So we now write this as from the above equations we have integral from a to b of electrostatic field as a function of position vector r dot dl, which is equals to minus, this term is what? Try to identify this term. This is potential at point B and this is potential at point A. So we can write now minus VRB plus VRA. Now see, as I said, if we take a point to be at infinity where the potential is supposed to be 0, so we now just modify, we now just have modification of this equation as, now this can be written as, if point A is taken at infinity where the potential is 0, that is RA is infinity, so it implies V at RA would be 0. So we now have A to be, you just write like this, A at infinity. So we now have this as here, we can write this to be integral from infinity to B. Integral from infinity to B of electrostatic field as a function of position vector r dot dl, which is equals to this is minus of VRB. Find that this term will become 0, and here A has been taken at infinity. So these are few changes in this equation. So here from you just have this negative sign here on LHS and just dropping this subscript B. So it is simply small r here. So in general, what can we write? In general, this is integral from infinity to r with negative sign e function of r dot dl, which is equals to potential at r simply. Or if we just have this alteration, limits gets altered, so we can have this r here and infinity here, electrostatic field function of r dot dl, which is equals to VR. So this way the potential, electrostatic potential at a certain point can be defined as the line integral of electrostatic field taken from the position of that point to the infinity. This can be said as electrostatic potential. तो इलेक्ट्रोस्टैटिक पोटेंशियल को हम कैसे डिफाइन कर सकते हैं किसी भी पॉइंट पे, कि इलेक्ट्रोस्टैटिक पोटेंशियल किसी भी पॉइंट r पे इलेक्ट्रोस्टैटिक फील्ड का लाइन इंटीग्रल होता है, जो कि किसी भी आर्बिट्ररी पाथ L बिटवीन दैट पॉइंट एंड द इंफिनिटी लिया जाता है. तो वो जो प्रोसेस है लाइन इंटीग्रेशन का, वो उस पॉइंट पे इलेक्ट्रोस्टैटिक पोटेंशियल डिफाइन करता है. सो विद दिस let's move on for the next. Okay students, so let's have next topic, physical meaning of potential difference and potential. अब हम इलेक्ट्रोस्टैटिक फील्ड के किसी भी एक सिंगल पॉइंट पे जो पोटेंशियल है उसका फिजिकल मीनिंग क्या है, और अगर उसी इलेक्ट्रोस्टैटिक फील्ड पे दो पॉइंट ले लिए जाए तो वो दो पॉइंट्स के बीच में अगर पोटेंशियल डिफरेंस है तो उसका फिजिकल मीनिंग क्या होगा. So this is the concern of this topic. So let's begin with, so here suppose we have three-dimensional rectangular coordinate system once again, where the presence of positive q charge is being considered at the origin of this 3D rectangular coordinate system x, y, z. Now suppose here we have 2 points A and B. So these are 2 points having position vectors as this RA and this RB. So these are position vectors simply. Now just join them through any arbitrary path L. Now take a point P on this path. The position vector of this point P is say R in general we take, and the electric field intensity at point this P due to this plus Q charge is along this. So as we know, if we take the test charge as Q naught positioned at A in the electrostatic field of this plus Q, and if we want to just move the test charge Q naught from this A point to B point following the path L. So what amount of work has to be carried out by the external agency or external source, that needs to be calculated. So for that, suppose here we place the test charge Q naught at point P. As we know, the test charge, presence of test charge here at P will make the application of electrostatic force as Q naught into E due to the electric field of this source charge. तो ये जो सोर्स चार्ज है वो इस Q naught चार्ज को जब हम P पॉइंट पे रखेंगे, क्योंकि वो Q naught पॉइंट इस Q चार्ज के इलेक्ट्रिक फील्ड पे होगा, इस वजह से ये क्या करेगा, उस पे फोर्स लगाएगा जो कि रेडियली आउटवर्ड होगा, और वो फोर्स हम लिख रहे हैं एज Q naught into वेक्टर E. अब ये क्या होगा, चार्ज यहाँ पे जो Q naught रखा गया है वो इस फोर्स की वजह से एक्सेलरेट होगा टुवर्ड्स दिस. नाउ वी डोंट वांट दैट चार्ज टू गेट एक्सेलरेटेड अलोंग दिस, तो हमें क्या करना पड़ेगा, एक्सटर्नली इस पे फोर्स लगाना पड़ेगा जस्ट इक्वल इन मैग्नीट्यूड टू दिस. तो हम इस पे फोर्स लगाते हैं टुवर्ड्स दिस. दिस इज द एक्सटर्नल फोर्स बीइंग अप्लाइड ऑन द टेस्ट चार्ज एट पॉइंट P. Now suppose this angle is theta, this angle we are having theta. Okay, so now let's move on. Now the work done to move the test charge Q naught through very small displacement dl by this external force F in the electrostatic field of this source charge we are calculating, and let that be represented by dW, and which is equals to force external force that we are applying so that there is no acceleration at all to move the charge Q naught. Now the displacement that we are producing by the application of this external force is infinitesimally small, say vector dl along this path. Now the force due to this source charge at this point we can very well write, and that will be electrostatic force. So here we just now have some modification here. So further we can write by integrating this equation between these 2 points, we can calculate the total work done. So here the W can be calculated by integrating this on both the sides. So integral from A to B, vector F dot vector dl, and this will be equals to, if we now have this value of F, and this F is minus of Q naught E. So just minus Q naught will be common, take it out, minus Q naught integral from A to B vector E dot vector dl. So this value we have already seen in a previous topic, we can write it further. This is equals to minus integral from a to b E dot dl. Now just dividing both the sides by q naught, we have this thing with us, and this simply gives us what? Potential difference between A and B. So we can write it as VB minus VA W upon Q naught. Here it would be better to write this between A and B, subscript AB, that will be much more clear. So potential difference between 2 points A and B in the electrostatic field can be defined as the amount of work done by the external agent between those 2 points per unit test charge. So this is the electrostatic potential difference between 2 points in the electrostatic field. Now moving ahead, being more specific about potential, so 1 point will be taken at infinity where potential is 0. So this way, later on, just eliminating or removing the subscript b, we can have the general equation of potential with us. So here, let point A is at infinity. Therefore VA will be 0, and hence we have, therefore, this thing W on Q naught, dropping the subscript as well, we can have V. So the electrostatic potential at a point in the electrostatic field is the amount of work done by the external source in moving the test charge Q naught without any acceleration. So that is electrostatic potential. तो electrostatic potential at any point in the electrostatic field को हम कैसे define कर सकते हैं? It is the amount of external work done by external source per unit test charge to move the test charge without any acceleration. तो इस तरीके से हम इसका physical meaning समझ सकते हैं. So let's move on. Okay students, so let's have next topic, units of electrostatic potential. अब जैसा कि हमने इलेक्ट्रिक फील्ड, इलेक्ट्रिक फोर्स के 2 यूनिट सीजीएस और वो सीजीएस में भी हमने इलेक्ट्रोस्टैटिक एंड इलेक्ट्रोमैग्नेटिक यूनिट्स देखे और फिर इसके बाद एसआई. तो यहाँ पे हम पोटेंशियल को भी देखते हैं कि क्या इसकी यूनिट्स होंगी. सो इन सीजीएस electrostatic system, we have its unit to be ESU or stat volt. Stat volt, electrostatic unit of potential or stat volt, which is equals to, we can write work done. Work done in CGS is written to be erg. So 1 erg upon charge, test charge. So charge is taken to be stat coulomb. So this way we can define this stat volt or ESU of potential. Now thereafter we can have in CGS electromagnetic system. Electromagnetic system, we can have EMU of potential or ab volt, which is equals to again 1 erg upon, what's the unit? Ab coulomb. So 1 ab coulomb. So this way we can have the definition of this. Now moving towards SI system, in SI we can have volt. So 1 volt is written to be 1 joule upon 1 coulomb. So this way, these are the units. In CGS ESU, electrostatic unit, stat volt, and 1 stat volt is equal to 1 hour upon 1 stat coulomb. And in CGS EMU, electromagnetic system, it is amp volt, which is 1 amp volt equal to 1 hour upon 1 amp coulomb. And in SI we simply have volt, which is 1 joule upon 1 coulomb. Now let's have the relationship. So for the relationship, we can have we can write first that stat volt and volt. So here you can write 1 volt equal to 1 joule upon 1 coulomb. So in 1 joule, how many ergs are there? 10 past to 7 erg upon, in 1 coulomb, how many amp coulombs are there? So here you can write 3 into 10 past to 9 ESU, electrostatic unit. So this finally gives you 1 by 300 stat volt. So just cross multiplying, 300 volts equal to 1 stat volt. So this is the relationship with us first. Now we can have the relation between this and this. Further, we can have 1 volt equal to 10 past to 7 erg upon 1 by 10 ab coulomb. Ab coulomb. So this finally gives us 10 past to 8 erg. So 10 past to, not erg, 10 past to 8 ab volt. So this way, this is the relationship between this volt and ab volt, and earlier we had volt and this stat volt. So this is the relationship, just to have the interconversion between CGS and that SI. So students, this is the end of today's lecture. So I hope you are enjoying the lecture. To have more excitement in physics, do like and subscribe the channel.